In this short lesson, we are going to look at the various types of gyroscopes, or gyros, commonly in use in aircraft. We will also look at gyro power sources and the advantages of each power source. Gyros can be classified by their function, construction, or power source, and each class can be divided into further categories. Let's look at each one in turn, starting with function. Gyros which are classified by function fall into two distinct categories. The first category is known as displacement gyros. These gyros are set up to measure angles, for example, degrees of bank, or degrees of pitch, or degrees of heading change. Displacement gyros can be divided into space gyros or tide gyros. Space gyros are unrestrained by any external force and are free to wander. Tide gyros, as the name implies, are tied or restored back to some required orientation by an external force. Finally, a subdivision of tide gyros is the earth gyro. Earth gyros have their orientation maintained by gravity. The second category of gyros classified by function is known as rate gyros. Rate gyros are set up to measure angular rate. By this we mean, for example, a rate of turn. Common rates of turn are 3 degrees per second or 6 degrees per second. We can see here then the full family tree of gyros classified by function. It will help greatly in the understanding of gyros if we remember this family tree. When it comes to classification by construction, there are 3 types of gyro in this classification. They are tuned rotor gyros, ring laser gyros, and fibre optic gyros. For information, the ring laser gyros work on the principle of comparing 2 light paths around a glass prism, and fibre optics are an extension of the ring laser principle. In this lesson, though, we are going to concentrate only on the tuned rotor gyro. The tuned rotor gyro is the traditional spinning disc type of gyro. The third and last classification refers only to tuned rotor gyros and describes the power source for the gyro. This will either be a pneumatic source or an electrical source, and we will look at this category in more detail shortly. But for the moment, let's turn our attention to tuned rotor gyros and how they work, firstly as displacement gyros, and secondly as rate gyros. To recap, we have seen that displacement gyros can be divided into space gyros and tide gyros. Both of these are 2 degree of freedom or 2 gimbal systems. They therefore allow the aircraft to pitch, roll and yaw without forcing the gyro out of its orientation. Let's look at how this is achieved. The gyro is mounted on a frame, which we will call the inner gimbal. We can see that this will allow the gyro to rotate around its own spin axis. At each end of the inner gimbal there is a pivot point. We can see one here. The pivot point on the inner gimbal bears on a second or outer gimbal, and this gives the outer gimbal the freedom to rotate around the inner gimbal. The inner gimbal or single gimbal is therefore said to provide 1 degree of freedom. Finally, the outer gimbal is pivoted in a housing which is fixed to the aircraft. This allows the housing, and also of course the aircraft, to move around the outer gimbal. The outer gimbal, or second gimbal, is therefore said to provide 2 degrees of freedom. So, we can see that by mounting the gyro within an inner and outer gimbal system, which in turn is fixed to the aircraft, there is total freedom for the aircraft to move around its gyro without displacing it from its orientation in any of its axes. Make a note, however, that by convention the degrees of freedom of a gyroscope do not include its own spin axis, and this is the reason why we say that 1 degree of freedom is provided by a single or inner gimbal, and 2 degrees of freedom are provided by an inner and outer 2 gimbal system. Let's look briefly at space gyros. A space gyro has gyroscopic inertia with reference to a point in space. This means that a space gyro is unrestrained by any external force. It is free to drift and topple, and, if it does, there is nothing to restore it back to its original orientation. Space gyros, therefore, have to have extremely low rates of real wander. This makes them expensive, and they are used only in high-technology applications such as inertial navigation systems, which are covered later in the course. Let's now look at the tide gyro. The tide gyro is also mounted in a 2 gimbal system, and because we ignore its spin axis, the tide gyro can be said to have 2 degrees of freedom. However, the fundamental difference between a space gyro and a tide gyro is that with the tide gyro, the rotor spin axis is controlled or tied in a desired position by an external force. In aircraft, the gyro is normally tied in the Earth's horizontal or vertical plane. An example of an instrument using a tide gyro is the directional gyro indicator, or DGI. A typical DGI from a light aircraft is illustrated here. An Earth gyro is in effect a tide gyro, but in the case of an Earth gyro, the rotor spin axis has its orientation maintained by gravity. As we can see, the Earth gyro is suspended in a 2 gimbal system, and again we can say that by convention it has 2 degrees of freedom. An example of an instrument using an Earth gyro is the artificial horizon, and we can see a typical artificial horizon from a light aircraft, illustrated here. The second category of tuned rotor gyros is the rate gyro. With this type of gyro, the gyro is mounted in a single gimbal, and a rate spring restricts freedom of the gyro in precession. The single gimbal allows freedom of movement around 2 axes, one of which is the gyro's spin axis. By convention, therefore, as the spin axis is not included, the rate gyro is said to have 1 degree of freedom. An example of an instrument using a rate gyro is the turn indicator, and we can see again a turn indicator illustrated here. To conclude, let's look at the power source for tuned rotor gyros. Gyros may be driven from a pneumatic power source, or they may be electrically powered. Let's look first at pneumatic power. If low air pressure is induced in a sealed instrument case, the low pressure will cause higher pressure air to be drawn into the instrument case. If this higher pressure air is supplied through a pipe of known cross-sectional area and directed at the rotor, it will cause the rotor to rotate. We can see this happening here. Low pressure in the instrument case can be achieved in 3 ways. Firstly, by using a dedicated engine-driven vacuum pump. Secondly, by utilising low air pressure produced in the engine inlet manifold. And thirdly, by the use of a venturi fitted outside the aircraft. The main advantage of the air-driven gyro is that it is independent of electrical power and is therefore not at risk from a total electrical failure. Electrically driven gyros are powered by alternating current. If the power source is DC, then an inverter will convert DC to AC, as the gyro rotor consists of the actual armature of an AC motor. The gyro rotor is therefore an integral part of the electric motor. The advantages to note of electrically driven gyros are: a faster spin speed can be achieved, which will give greater gyro rigidity and reduced errors. A constant rotor speed can be maintained, giving greater accuracy. The gyro can be sealed in an airtight case, which will prevent dust and moisture causing excessive wear on the moving parts. Operating RPM can be more rapidly achieved, giving greater efficiency. This ends the lesson on types of gyroscopes. A short summary follows. A gyro is classified by its function, construction, or power source. Gyros which are classified by function are displacement gyros or rate gyros. Displacement gyros can be divided into space gyros and tide gyros. An earth gyro is a tide gyro, tied by gravity. Gyros classified by construction are tuned rotor gyros, ring laser gyros, and fibre optic gyros. A tuned rotor gyro is the spinning disc type of rotor. Gyros classified by power source are tuned rotor gyros. By convention, the degrees of freedom of a gyro do not include its own spin axis. Rate gyros are set up to measure angular rate. A space gyro is said to have 2 degrees of freedom in a 2-gimbal system. A tide gyro has 2 degrees of freedom in a 2-gimbal system, where the rotor spin axis is tied in a desired position. An earth gyro has 2 degrees of freedom in a 2-gimbal system, where the rotor spin axis is tied by gravity. A rate gyro has 1 degree of freedom in a single gimbal system and uses a spring system to restrict precession. An example of a tide gyro is a DGI. An example of an earth gyro is an artificial horizon. An example of a rate gyro is a turn indicator. The advantage of an air-driven gyro is that it is independent of electrical power. The advantages of electrically driven gyros are that a faster spin speed can be achieved, giving greater rigidity and reduced errors. A constant rotor speed can be maintained. The gyro can be sealed in an airtight case, and operating RPM can be quickly achieved.